sustainable rate. So I was kind of thinking, what would sustainability mean to me in my work? And I wanted to kind of, you know, think about the processing chain. So I work with nanomaterials and solution processing. So the various steps along the way, from material sources, where do we get it from? How do we process the materials, up to the devices themselves? What does sustainability kind of mean to me in my work? So the first thing I was thinking about, sustainability, it kind of, it evokes thoughts of like recyclability, or, if you get materials out of the ground, are they biodegradable, for example? So that's kind of what sustainability means. But I want to kind of think about, when it comes to our material sources, just how sustainable or reliable is the supply of materials, of where we get them from. So we don't need to, the motivation for this, we don't need to go back too far. In 2020, the pandemic hit. This caused absolute chaos to the global supply chains. GDPs fell through the floor, and we're probably still dealing with the outfall of that. A year later, these guys decided to park their shipping, their container ship in the Suez Canal, which is a major bottleneck for the transport routes. And this caused absolute chaos as well. This was only a year after the pandemic. And then if we look at this week, the smartest, or the dumbest man alive, who's in charge of the wealthiest empire in existence, decided to pump and dump the stock market, leading to something that a Wikipedia page was created within hours. So the question I want to ask is, yes, so how reliable is it if we want to get materials? How sustainable is it if we want to buy them, if we want to use them? How reliable is it? Now, typically, the measure of this is abundance. So if we take maxines, for example, these are two-dimensional materials that are exfoliated from a max phase. They are early transition metals mixed with an A phase of aluminium, silica, and phosphor, etc., and then terminated with a carbon nitride. And these are typically described as sustainable materials because they come from abundant elements. When it comes to battery electrodes, for example, there's also things like magnesium or silicon, and people argue that these are earth-abundant materials. But typically, sustainability is associated with abundance. And the way you argue this is, you go to Wikipedia, you sort the abundance column from top to bottom, and you say, okay, we have magnesium as an electrode, and it's 1, 2, 3, 4, it's the seventh most abundant, so therefore it's sustainable. However, these elements are not evenly distributed across the world. And when it comes to supply chains and things, we need to note that abundance of materials does not equal access to materials. So if we look at where all our materials come from in the EU, we see that 92% of all our niobium comes from Brazil. Our cobalt and tantalum come from the Congo. All of the platinum group metals come from South Africa. A lot comes from China then as well. So magnesium, 91% of our magnesium comes from China. So if you want to build magnesium batteries and somebody decides to crash a tanker down in the Suez Canal, then all of a sudden we're going to have problems getting material. So if we take the abundance here on the x-axis, parts per million for every element, and then we plot how much we import into the EU, if it truly was something like abundance is tied to availability, then we'd expect an inverse relationship here. But instead, what we find is that some of the most abundant elements we are importing almost 60 to 100% of. So all our magnesium, our titanium, this is natural graphite. We get most of that from China. All of the rare earth elements and platinum group elements, we have to import all of these. But surprisingly, also things like nickel, phosphor, manganese, these are all imported as well. And then some of the least abundant elements we're almost completely self-sufficient in. So things like gold and tellurium, selenium, the chalcogens, we can produce a lot of these ourselves. If we also look at the largest supplier fraction, so this would be a measure of how monopolized a supply route is. We see, and this is against abundance again, we see things like magnesium, this all comes from one supplier basically. And so does things like strontium, rubidium, niobium, boron. All our boron comes from Turkey. So these are highly concentrated in one supplier, even though they're extremely abundant. So we need to worry about things like how much are we importing and where are we getting it from? How diverse are our sources? So what we did is we created an equation where we assess how resilient the supply of every element is. And this supply resilience is related to things like how much we import, how much we export, domestic production, recycling rates, and how concentrated the supplier fraction is. And this gives us then a number which is grading each material, each element here between 0 and 100. So the first thing that we can see that jumps out here, all of these early transition metals that form the basis of magazines, for example, we depend on imports for basically all of these, along with the rare earth elements down the lanthanides. The platinum group metals also, we are fully dependent on those, including like manganese, lithium as well. This all comes from Chile, beryllium from the United States, magnesium comes from China. So the things that we are actually mostly independent and self-sufficient are the chalcogens and then fluorine and chlorine in the halides. Our bromine and iodine are all fully imported. Bromine comes from the Dead Sea and is imported from Israel. And a lot of our iodine comes from, 66% comes from Chile. So when it comes to actually making things like nanomaterials and 2D materials, if you're making perovskites, for example, you're heavily dependent on bromine and iodine. So, you might want to, these are things that we need to be cognizant of. So looking at the largest supplier fraction again, so this is the degree of monopolization, and this is now plotted against supply resilience. So how easy it is, how locally we produce our materials. If we look down here at the bottom right-hand corner with these elements, these are there's low concentration, so we have a diverse number of suppliers, and because it's high resilience, we are relatively self-sufficient. So we're self-sufficient with a large number of suppliers for things like copper, lead, sulfur, cadmium, tellurium, gold, selenium, silver, and hafnium. Hafnium is actually derived from the nuclear industry in France, but they get it from their zirconium, so it's a byproduct of that. So we have all the hafnium we need, which is good, because hafnium forms a very high dielectric constant insulator, and also hafnium sulfide as well is a good semiconductor. Then if we look up here in the top left, these would be a concentrated number of suppliers. So for example, and we'd be highly dependent on imports. So if we look up here at this graph, we see that all our rubidium comes from China, our boron from Turkey, magnesium from China. Again, the platinum group metals are from South Africa. All our lithium, nearly 80% almost, comes from Chile. Then things like gallium as well, almost all of that comes from China. China again, Chile for iodine. Most of our cerium comes from Russia, nothing to worry about there. Antimony from Turkey, cobalt, aluminium, etc. So a lot of these materials that we commonly use, especially for the synthesis of two-dimensional materials, we're highly dependent on a small number of suppliers. If we look at conductive nanomaterials, most of these elements down here are the maxines. I wanted to put them in to show that while the conductivities may be high, because we're dependent on things like titanium, vanadium, molybdenum, tantalum, and niobium, this makes the actual supply of the fundamental elements in these materials quite unstable and quite unreliable. If the A phase in the maxines, it uses something like gold, the maxine becomes more resilient. And while the conductivity tends to be lower, you have a better chance of being able to produce this material outside of global supply shocks. Then, of course, we're self-sufficient in silver and gold, and we can create graphene using a large number of sources. So high conductivities can be achieved using things like silvers and golds. When it comes to dielectrics, then, we have the dielectric constant here plotted against supply resilience for a bunch of different materials. Things like boron nitride, we are completely dependent on boron from Turkey, so this is a low supply resilience. Same goes for, again, titanium oxide, that comes from China, I believe. Barium as well, strontium, even though these have extremely high dielectric constants to synthesize this, perhaps the supply of material itself is not very reliable. But if we look at things like hafnium oxide, again, we get all that from France, so that's quite stable. Cellulose, if it's hydrated or dry, has a high dielectric constant, and that's producible everywhere. And then we have the aluminosilicates, which we can dig out of the ground here in the Alps in particular, like MMT, kaolin, mica as well. So these are quite resilient because we produce them here in Europe, and they have reasonably good dielectric constants as well. When we move to look at battery electrode materials, this is the theoretical capacity associated with individual elements, because even if you're using a compound like MOS2, the sulfur atom is doing all of the work. So molybdenum actually doesn't contribute that much. So that's why these elements here are plotted, the theoretical capacity against the supply resilience for the individual elements. So again, we see the highest resilience, the ones with the capacities like cadmium, gold, tellurium, sulfur, cadmium, sulfur, calcium batteries, high theoretical capacities, and we produce all of that here. And then the supply resilience, how secure our supply lines are, tailors off. So lithium, again, all of that comes from Chile. So this will have low resilience, even though the liquid metal of lithium has quite high theoretical capacity. So that magnesium paper that I showed you at the beginning, even though it has a decent theoretical capacity, the supply of it is not very reliable. So we would need to think about looking at more European-centric materials if you want to guarantee security of supply. So the take-home messages from this part would be: abundance of a material tells us nothing about how we can get our hands on it. We are self-sufficient in our chalcogens, some of the halides, hafnium, sodium, cadmium, tin, tungsten, chromium, and indium, and of course gold and silver. And we are fully dependent on global trade. So this is something you need to keep in mind if you're working with these materials. Rare earths, platinum group materials, boron, bromine, titanium, molybdenum. So some ones that are quite common, in particular, molybdenum was very surprising to me, given all the work that's been done on MOS2. So moving on then from the material sources to the bit further up the processing chain, I want to talk about a solvent called styrene. And this is a solvent that we can produce from cellulose and biomass. So if you take biomass and cellulose using pyrolysis, you can produce this molecule known as levoglucosanone, and yields up to 40%. Then, through hydrogenation, you can convert this levoglucosanone into dihydrolevoglucosanone, and that's known commercially as styrene. Now, the reason we would want to do this is not only because it is a sustainable solvent, but also because the solubility parameters, so the surface energy, for example, these are very similar to solvents like NMP, DMF, and DMSO. And these solvents here, if you go back, 10 years when all the processing of 2D materials in liquid phase was begun, then they were using NMP and DMF and all these toxic solvents simply because these solubility parameters were so well matched to 2D materials like graphene and MOS2. So now we have a solvent here, styrene, that is non-toxic, and this can now serve as something that can substitute these if we know how to process it. So I'm going to talk about the solution processing of it, so the processes that we use in terms of handling, and then I'm going to speak about processing carbon nanotubes and graphene in styrene, and then how do we make thin films and what are the properties of those from styrene. So just a quick recap on what liquid phase exfoliation is. We take a sonic tip or a sonic probe, we put it into a solvent that contains our layered crystal, and we excite this here, and this applies sonic energy into this dispersion. And the vibration frequency of this probe, it creates bubbles and cavitation, and as the bubbles collapse, they transfer stresses to the material inside in the solvent. So this creates shear effects, it creates compressive waves, we get fragmentation of our nanosheets, so they begin to shatter, and also edge effects cause peeling. So what happens here is you're delaminating, you're breaking up the crystal, and this allows you to generate nanosheets. So when you do this in a dispersion that is an organic solvent or water surfactant, we can produce stable dispersions of nanosheets. However, if we use solvents just like pure water, for example, with graphite, this is badly matched. So all your material will just crash out and it's not stable. Now, because this we can use surfactants and we're matching surface energies, it doesn't really matter what starting crystal you could take. This process works for basically all layered crystals, all across semiconductors, conductors, dielectrics, superconductors, etc. It doesn't matter what the material is. You can process it using this technique. Now, this is quite a mechanically aggressive method, but when you look inside using TEM, what we find are pristine basal planes. And generally, the defects that are associated with these nanosheets are associated with the edges themselves. This technique is also scalable. You can use shear mixing here to generate liter scale quantities. So in a similar method, the material is pulled in through a rotor, and the shear effects caused by pulling the material in through here, pushing it out, cause delamination. Oops. So typical powers for the sonic tip for processing carbon nanotubes are about 5 watts. So we took styrene we processed just pure styrene at 5 watts for up to 6 hours just to make sure we weren't seeing any changes in the solvent. And 5 watts, these are UV vis spectra, there's no changes. If we sonicate the solvent, the pure solvent at 50 watts, which is a typical power that you use for processing 2D materials, what we see is drastic changes, particularly in the visible part of the spectrum here, where for processing times up to 8 hours, which is a pretty common processing time, almost the entire, from 600 nanometers downwards of the visible spectrum is now dominated by what we've created in here, this degradation product. Now, when you're applying the sonication process, it is quite mechanically aggressive. It's energy intensive. So this is always cooled with an ice bath or with some sort of coolant system. So we did that this time. So we weren't sure that it was the heat that was causing it because in theory the solvent should have been cold. So we took a hot plate and an oil bath, and we just heated the styrene itself at 175 degrees because this is now below the boiling point of 200. And what we see is the same changes in the spectra occurring just by heating. So what's happening during probe sonication, the localized heating at the styrene around the side of the tip is causing it to degrade into something in here. So to investigate this a bit further, we did TGA for the pristine styrene and also for the sonicated styrene and heated styrene. Let me just see if this video will play here. This is the video now of the TGA process. So let me just see. Yes, this red line that is moving from left to right is the mass and is moving against temperature. So the important thing here is that this is normal behavior for a solvent. It just evaporates off normally, no residues are gone, and we get a nice clean boiling point. Now, if we do the same thing for whatever this degradation product here is, we run the process again. So this is the mass of the solvent. This is it starting again. The mass of the solvent against temperature. And in the video, what we see is we see some boil off of the solvent, which is the plain styrene component that's gone. And then there's clearly a solid component left. And then that kind of combusts and turns into an ugly black donut. So we clearly have two components in here, one of which is styrene itself, clearly, and another is some sort of solid that is dissolved inside in the styrene. So to analyze what these compounds were, we did NMR. This is NMR of a clean styrene spectrum. And this here is NMR then of this red styrene degradation component. And then through some wizardry known as a cozy spectrum, Marta Corvu here at Cinemat was able to deduce that this is what the compound looked like that styrene is degrading into. So this is known as a self-aldol condensation of styrene, and typically you need a base to start this reaction, but in this case we're actually able to induce it by heat, and this is the dissolved solid that we find mixed in with the styrene in here. Something else that we noticed is that if this dispersion gets wet, if any water gets into it, it causes rapid precipitation, then an exothermic reaction and rapid precipitation of this solid out of solution. So this is pretty important if you're actually going to be processing your material using sonic tip, because you're going to be creating this along with exfoliating your materials. So as we move on to looking at carbon nanotubes, we need to be careful to work at a sonication power that's only 5 watts. We picked an initial sonication time of about 3 hours and a starting concentration of 0.25 mg per mil. So the carbon nanotubes that we're using are from P3 Carbon Solutions. They're a company in the States. The typical diameters are about 1.5 nanometers and they arrive in bundles. So we want to, because the masses are typically quite low that you work with, we wanted to produce a dilution series. So we started with a very concentrated, known concentration of carbon nanotubes and diluted it down to get UV vis spectrum. And then by plotting the value at 660 nanometers, or 600 nanometers, I should say, against concentration, we're able to extract an extinction coefficient, which then means regardless of how low the concentration is, we can use UV-Vis to determine the concentration of our material. So then if we work with something called the reduced transition energy, so this the value of working with this is that it tells us the reason why we work with, plot this against reduced transition energy is because values around 2 peaks around 2 are associated with semiconductor transitions, peaks around 3 are associated with metal transitions, peaks around 4 are the semiconducting 3-3 transitions. So what this tells us that the majority of our dispersion, when we create this in styrene sodium cholate, we produce large bundles of primarily semiconducting nanotubes. Now, we also produce dispersions in IPA and sodium cholate. And what we found was that these nanotubes, the width of this S22 peak is a measure of how many bundles there are in your dispersion. And both of these have fairly broad peaks, indicating that we still have quite a lot of bundles. Interestingly, if we centrifuge our material in styrene, just pristine styrene here, it falls off at a rate of, it falls off at an exponent of minus 0.35. And if we disperse the same amount of nanotubes in the sonicated styrene with the self-aldol condensate in there, it's actually more stable. So that dissolved solid appears to be conferring some sort of, improved stability to the carbon nanotubes. So we did AFM then. We did AFM in this dispersion, and what the important thing that we find here is that we are producing individual nanotubes. They're visible quite here from the height data, and we're also producing bundles. So even though this was just kind of a guess at the sonication time and concentration, we do produce nanotubes, so it is possible to produce them in there. We just need to figure out the conditions under which we can maximize the amount of nanotubes, individual nanotubes, that we can produce in styrene. So we did a sonication time dependence where we used the same sonication power of 5 watts, and we held the initial concentration constant at about 0.25 mg per mil. So we can see as we go up from 1 hour, 2 hour, 3 hours, up to 6 hours, that the distribution of diameters of nanotubes falls off then and kind of accumulates around a constant data here our constant diameter after about 4 hours, and that's about 4.8 nanometers. So then we did the same thing for an initial concentration dependence. We held the sonication time constant at 4 hours. Again, we used a 5-watt sonication power. And then we varied the concentration from 1 mg per mil down to 0.1 mg per mil. And what we find is, again, a wide distribution at 1 mg per mil. And this starts to move to the left here, the diameters. So there's clearly some sort of change as well in diameter, where it becomes constant below 0.1 mg per mil at about exactly the same value as we found for the initial sonication time dependence. So what we have here is a relationship between the diameter of the debundled nanotubes and the starting concentration. So this suggests that there are 2 regimes here. One where it is debundling dominated scaling for concentrations above 0.1 mg per mil. And then we have a van der Waals dominated regime below 0.1 mg per mil. So what do I mean by these 2 regimes? Well, the debundling dominated scaling regime is where there is a lot of material in the dispersion. There's contact between the bundles, and the mechanical energy from the tip is transferred bundle to bundle to bundle, which allows them to debundle this way. So to quantify this and to fit the data, we take the number volume, which is the number of nanotubes or number of bundles per volume, which is equal to the concentration, the milligrams per milliliter over the average bundle mass. So reformulating this equation gives us this value here, which is the diameter is now in terms of the concentration, the density of the nanotubes, and the length of the bundles. Now, we didn't have this data, so we had to go back to our AFM. And what we found was when we counted the lengths of the bundles, we found that there seems to be a mix of large and small bundles. The large bundles tend to have an average diameter of about 2.5 microns, and then small bundles tend to have a diameter of about 860. So by fitting the data that we have here, this is the same data again, just on a log-log plot of the diameter versus starting concentration. We fix L bundle to be 2.5 microns, and this is the solid line here, and it gives us a number volume of 3.1 by 10 to the 18 nanotubes per meter cubed. So the inverse of this value here would be the average volume that is taken up by a single bundle. And this is this volume here, 3.2 by 10 to the minus 19. And this gives us then, this, it turns out, is the volume of a sphere whose diameter is 848 nanometers. So that's pretty close to the length of the bundle of the small tubes, or the length of the small bundles. So what this means is that the small bundles are effectively isolated within their own pervaded volume. So to analyze this a little bit further, if we assume that each bundle occupies exactly its own volume, then what we do is we put this sphere volume back into this value here, and this equation then collapses down to this simplified equation here. So by setting the length of the bundle to be 860, we get this dotted line. And the fact that our data points lie below this line means that our system is dilute. So the nanotube bundles, the small bundles, are not in contact with each other. So this doesn't tell us much about individual nanotubes. So to analyze this a bit further, we go to our AFM stats again, and we define an individual nanotube as anything with a height below 2.5 nanometers. We define a small bundle as something with a height that is the diameter of the small bundle plus one standard deviation, which is 6.2 nanometers. So anything then between 2.5 and 6.2 nanometers is a small bundle. And then anything larger than 6.2 nanometers is a large bundle. So we find the van der Waals dominated regime, which is below 0.1 mg per mil. We get individual nanotubes, a yield of about 16%, which is about the same as that of large bundles. And then down here in this regime, we are dominated by small bundles with about 68%. If we move up above 0.1 mg per mil, we're in the debundling dominated regime. So this is where there's a relationship, an inverse relationship, I should say, between large and small bundles. And then the individual nanotubes fall off as 1 over C, which we can understand as taking the number fraction of individual nanotubes, and we multiply that by the total number per volume. We fit that to the equation that we found on the last slide, and we get good agreement here showing that the number fraction will fall off as the concentration increases. So the take-home message here for the carbon nanotube exfoliation is that we're producing in Cyrene individual nanotubes at a yield of about 16%. So if we move on now to graphene, once again, we're going to take initial conditions that are common to exfoliating powdered materials using this liquid phase exfoliation process. This time, even though we know we're going to be converting and creating the self-aldol condensation, we're still just going to go ahead and do it anyway. So sonication power of 50 watts, common sonication time of about 6 hours, and initial concentration, sorry, that should be 30 milligrams per milliliter. Now, the problem is when you do this with a bulk powder, you're left with a polydispersion. You have large and small nanosheets all mixed into the same dispersion. And what we want to do is find a way to isolate these out because we want nanosheets of a certain size and certain thickness. And ideally, we would like to produce monolayer rich dispersions. Now, the easiest way to do this is using liquid cascade centrifugation, where we take this sonicated stock directly out here, we centrifuge it at a low speed, and this will contain all of the unexfoliated material. We discard this, and then we take the supernatant up here, we centrifuge that again at a higher speed. Then we'll have the sediment down here that will contain nanosheets with a certain length and a certain thickness. This will be sample 1, for example. Then we take the supernatant and we continue this process up, and we iteratively then get progressively smaller and thinner nanosheets. So we did this for the graphene exfoliated in Cyrene. This is a UV vis spectra here where we can see that the low speed centrifugation produces thick nanosheets, which is related to the relationship here between the ratio of the peak to the long wavelength plateau. And we see that as the centrifugation speed increases, we get thinner and thinner nanosheets. So once again, we did AFM statistics on the various centrifugation speeds. This is just 2 examples here. So the low speed, 3K RPM, we see a wide distribution in nanosheet lengths. And at the high speed centrifugation, we see a very narrow distribution in length. If we look at the layer number as well, that's n layer number here, wide distribution in layer numbers at low speeds, and a very narrow distribution of layer number at high speeds. So by plotting the nanosheet length and width, which is a proxy for the area of the basal plane, against the nanosheet thickness, or sorry, layer number, for all of these centrifugation speeds, we get a cloud that looks like this. So all the high speed, thin, and small nanosheets are down here, and all the thick stuff is up here. So these are representative AFM images, but we see even up here at the top right, where the nanosheets are quite large and quite thick, you still get nice kind of clean basal planes in there. So you are producing nanosheets, they're just extremely large and chunky. Now, one other thing to note in here is that even up at speeds of 11.25 kRPM, we find no monolayers. We find perhaps one bilayer, maybe two trilayers. So we're not producing really, or we're not producing any monolayers, bilayers, few layers, but it may be the case that they're in the dispersion, but these centrifugation speeds simply can't get them out. So plotting the distribution of layer number, distribution of length against the g-force that we're centrifuging at, we find an inverse relationship which is proportional to 1 over the square root of g. So to investigate this a little bit further, we can use the Stokes equation, which is for particles moving in viscous media. In this case, we're going to relate the Stokes diameter to the average nanosheet length. So I've taken some data from this reference down here, Back is it all, for graphene exfoliated in sodium cholate and also graphene exfoliated in NMP. And what we find is that these triangles here with a viscosity of 1 for water, sodium cholate, you find good agreement with a terminal velocity of 5 by 10 to the minus 6. So usually the problem with using this equation is that it's difficult to get a terminal velocity out. So if we want to assess the effects of viscosity, I'm going to hold this terminal velocity constant and then increment the viscosity up to that of NMP. And that gives us this dashed line here, which we find qualitatively agrees with the NMP data from reference 1. And then if I set the viscosity to that of styrene, which is this dotted line, again, agreement's not great, but it is qualitatively similar. But what is good about this is that it tells us, because of the viscosity, the increased viscosity of the styrene, we need a 10 times increase in the central RCF, in the G-force, to achieve similar lengths. So if we want a length of, for example, 500 nanometers that we have here in water, we need to use a 10 times higher G-force on the centrifuge in order to produce something of similar length. So further analysis here, we plot the length of the nanosheets versus the thickness for the aspect ratio. We find in water, we get an aspect ratio of about 55. And then with the higher viscosity solvents in styrene, we get a much lower, almost a half. The aspect ratio is almost half that of that exfoliated. Now, the reason why aspect ratio is important is because when you have thick nanosheets and you print a network or you deposit a network of MOS2, for example, mobility tends to be quite low because you have a jammed system of nanosheets and they don't sit very nicely on top of each other. When you have very thin nanosheets with a high aspect ratio, we get very, very nice overlap areas. You get good junctions here where the nanosheets sit very nicely on top of each other. This leads to good charge transport between them and much higher mobilities, almost 2 orders of magnitude higher. So if we're producing nanosheets in styrene, the problem is the aspect ratio is a bit higher, so we're going to have this problem here of a jammed system. Now, if we plot the area of the nanosheets here versus the thickness, we can then fit this using this equation here, which gives us the characteristic lateral size of a monolayer. Typically, this is in around 30 to 40 nanometers for graphene. And then this beta here is an exponent relating length to thickness after exfoliation. And this tends to get much, much smaller then for styrene as it falls off compared to water. So this just gives us a measure of the relationship between aspect ratio for exfoliating and higher viscosity solvents. What we would like is a much higher beta here because this would give us higher aspect ratio nanosheets. So if we want to achieve a monolayer enriched dispersion where the average distribution is approximately 1 for layer number, for centrifuging in water, we would need a G-force of about 30 kRPM. For NMP, we would need a G-force of about, say, 150 RPM. And for Cyrene, we would need to go up to about 1.5 million RPM. So as far as I know, these centrifuges are only, you only get these in molecular biology labs. And generally, the volumes that you put in here are way too small to be doing anything like creating inks. If we look at the yield, which is the total mass of the fractions that we got out of at every centrifugation, we find that because most of the mass that you create during sonication is large particles, during the first centrifugation step, you pretty much lose all of it at low RPM. So if we sum up the masses across all of these centrifugations, we get about 1.8% total. So this is much lower than working in NMP or water, but it is slightly higher than working in bath sonication, which is also quite an inefficient process. So we wanted to look at inkjet printing of Cyrene. So the issue here is that when you want to inkjet print, you generally need particles that are about 20 times or 10 times smaller than the nozzle diameter. Now, if you're working with a Dymatics printer, like a lot of people are, they recently changed their cartridges, and the nozzles are now 10 microns in diameter. So they used to be 20, so this adds an additional constraint on top of this. So what we did is we took the highest centrifugation sample, 11.25 kRPM. The yield at this concentration was 0.5%, which gave us about 0.5 mg per mil in 4 milliliters. So it wasn't really much at all. We then printed this material. So this was onto silicon dioxide. We found some kind of coffee staining effect, but that can probably be resolved by tuning the surface energy by treating the surface of the silicon dioxide. The problem is Cyrene is a high boiling point solvent. The boiling point, as we saw, was about 200 degrees. So to remove the solvent, we performed annealing at 300 degrees. And because of this self-aldol condensation, we found this, if you remember the TGA that I showed you, as you begin to boil off this self-aldol condensate in here, turns into all of these really nice crystals that look like Christmas cards, which is great for sending to your family in December, but not so great if you want to start printing. So we moved to spin coating instead. And if you're going to be spin coating, you need larger masses of material. So we had plenty of carbon nanotubes on hand. And we spin coated a carbon nanotube network onto these electrodes here. So this is a carbon nanotube network as spin coated. Then following annealing, we were able to remove most of this solvent. But again, because of this condensate in here, this is what the electrode and thin film looked like afterwards, which was pretty nasty. So as the conductivity here, we measured it as the temperature goes up, it begins quite low because there's clearly quite a lot of solvent still trapped in here between the nanotubes. And then as all the solvent boils off, we reach a plateau at about 1,000 Siemens per meter. As a control, we also created some carbon nanotubes in IPA. We spin coated these onto these same electrodes, and because it's IPA, it evaporates off fairly quickly. And at room temperature, you can achieve conductivities that are about a factor of 10 higher. So we also looked at the transmittance because people use carbon nanotubes for transparent conductors. And then this is actually pretty interesting because as you go increase in temperature, it doesn't begin to affect the transparence, or the transmittance, I should say, too much up until you reach values of maybe 300 degrees. So the conductivity is relatively constant. It's slowly growing up until transmittances of until this self-aldol condensate begins to turn black. But we can achieve conductivities of about 500 Siemens per meter while maintaining a reasonable transmittance. So the take-home messages, if you want to work in Cyrene, is that it undergoes this condensation when exposed to heat. So you need to work at low temperatures to avoid it, if possible. Carbon nanotubes can be debundled into individual nanotubes, but the yield is about 16% for concentrations below 0.1. We can exfoliate graphene into nanosheets, but they tend to be larger and thicker because of, again, the viscosity of the Cyrene. Inkjet printing is probably not viable because of the low yield of very small nanosheets that are printable. And then when you go to anneal away the material, we have this reaction again, which creates these nice crystals, but not good for conductivity. But we can also produce reasonable conductivities for annealing temperatures up to 250 degrees while maintaining transmittance. So the last very quickly thing I want to show you is devices. So we had a a master student came to me recently and said she wanted to produce some sensors by coating molybdenum disulfide onto a fiber. So we wanted to, if we want to do a coating with a two-dimensional material, we need large area thin monolayers. And if you want to do that, if you want to create nanosheets that have very, very large basal planes and are monolayer thin, you need to use electrochemical exfoliation. Now, this works by intercalating compounds in between the sheets. And when you put them in a sonic bath, then you break them off gently and you get these large area monolayers. Now, this is good for when you're making networks because they sit very nicely on top of each other. You get all this van der Waals bonding and you create a strong conformed network. So she wanted to use TPU fibers for sensing applications. So these were first coated using drop casting directly onto the fiber. And what we found was poor interfacial adhesion between the MOS2 network and the TPU. So the TPU underneath basically moved independently of the MOS2, and it caused all this pile up and all this breakup. It was pretty ugly. The strain of the TPU itself caused the entire structure to split and coil. So, because we're talking about sustainability, she wanted to use a sustainable substrate, sustainable fiber. So, what better to use than something like keratin or hair, which is a fibrous protein that we are continuously producing all of the time. Our hair cycles, funnily enough, they work on different rest and growth periods. Facial hair grows at a rate of about 6 weeks, scalp hair about 6 to 7 years, armpits generally last about 6 months, leg hair about 2 months. So we have quite a little factory here from people that we can produce with growth rates of about 0.3 millimeters a day, which funnily enough works out to about 8 meters per lifetime. So lots of material continuously being produced. So we did the same thing. We drop cast MOS2 onto hair, and what we found was it actually coated it way, way nicer. So you can see the keratinous structure of the hair along here. We have an MOS2 coating on the outside, and because the MOS2 is large and thin, what we find is really nice conformality onto the structure of the hair itself. So this allows the MOS2 to move with the hair as it bends and stretches. So we coated one of these hairs. We calculated then the conductivity of the MOS2 along the hair, and it worked out at about 70 Siemens per meter. And this is almost exactly the same as the conductivity that we found for MOS2 on silicon dioxide. So it doesn't matter that we have this cylindrical structure of MOS2, we can achieve exactly the same conductivity. She managed to bend almost by accident the hair to a 90-degree angle, and this only resulted in an increase in the resistance of about a factor of 1.3. So this is where she is at the moment. This is just something I wanted to show you about sustainable substrates. We will be using these probably to produce maybe pH sensors or something, but this is future work. So on that note, I'd like to thank all of my colleagues here at Cinemat for all the help on the work that I've shown you here today. All of the international collaborators as well, from Czech Republic, from Germany, Ireland, and Austria. And then I'd also like to thank the funders for all the money, and thank you for your attention.
So thank you very much, Adam, for the interesting talk and also the point of view in terms of materials of sustainability. I don't know if there exist any questions from the audience. I have 2 points that I'd like to ask you. So in terms of the materials processing, in terms of vision in Europe, that a good dielectric in terms of the materials will be like as hafnium disulfide, and in terms of semiconductor molybdenum disulfide, right? These are two good options to put on.
Yes, yeah. So I mean, almost all of the semiconducting work on MOS2, it's all done on MOS2. There's thousands of papers on it at this stage. But 56% of our molybdenum comes from the United States, so nothing to worry about there, right? So the thing is, if you take something like hafnium, we produce all of that ourselves. The mobilities are actually reasonably similar for hafnium sulfide compared to molybdenum disulfide, and we produce all of the hafnium ourselves. And we can also convert hafnium sulfide into hafnium oxide. So we have, a self. We have hafnium with its own oxide and its sulfide, and we have a dielectric and a semiconductor. So, that speaks to something like contained electronics.
Yeah. And the other point was about the DSC image. So it's really interesting what you made with the video and so on to see the sonicated and the pristine styrene, basically. And did you analyze the byproducts of the sonicated styrene? So that you had in the crucible, did you analyze it?
Yeah. The analysis that we've done so far is just the identification through NMR, and it is this dissolved solid, this self-aldol condensate from styrene. I've been looking through the literature trying to. I mean, if you sonicate styrene, you think somebody would have mentioned this, But the thing is, the only thing I can see mentioned in the literature is in one paper on it, and they said, "Oh, by the way, this condensation can happen, so just don't use elevated temperatures." So that's kind of all they said. So to deal with it, just avoid it. And I think in every paper, you know this yourself. In every paper on styrene, people just use tip sonication, and then they show this UV vis spectra afterwards, and there's no mention of they just use styrene before and then sonication with material afterwards. So there's no way to tell if there's anything mixed in there, because you can't just subtract off the styrene background because you now have this condensate in there.
Yeah, sure. So if no questions, we also need to move on. So thank you very much, Adam, once more time.